Hello students. So today discussion is about nuclear chemistry, one of the main chapters students in this toppers. So nuclear chemistry. So what this chapter deals about? Ultimately it is there in the name only, nuclear chemistry. What is the meaning? So this chapter is going to deal about the nucleus, okay, radioactivity about the nucleus, the reactions which are taking place involving the nucleus, all comes under this nuclear chemistry, the stability of the nucleus, everything. So let's see the introduction. Nuclear chemistry is a branch of chemistry which deals with the reactions involving atomic nuclei. It came into the prominence after the discovery of radioactivity. Students, listen, you already know the chemical reactions, yes or no? So what is the difference between the chemical reactions and nuclear reactions? What is the fundamental difference? Chemical reactions takes place by electrons. Nuclear reactions takes place by involving nucleus, that's it. So first of all, how chemical reactions takes place? Either by losing electrons, gaining electrons, or sharing electrons, yes or no? That's how the chemical reactions takes place. How does the nuclear reactions takes place? Nuclear reactions takes place by involving protons and neutrons also. Why? Because what the nucleus contains? Nucleus is made up of protons and neutrons. Yes or no, students, right? So that's why the reactions involving these subatomic particles also called as nuclear reactions, that we are going to discuss in this chapter. And as well as under the chemical reactions, what is the newly synthesized material is called as? It is called as a compound, a new compound. For example, hydrogen combines with oxygen. What do we get? Water. Carbon plus oxygen, carbon dioxide. So a new compound is synthesized. Then what are the new synthesized product is called as the nuclear reaction. In the nuclear reaction, a new element is synthesized. Understood? Why? Because protons and neutrons are changing. Yes sir, if proton changes, element only changes. An element with two protons is called as helium. If it has only one proton, can we still call it as helium? No, it is hydrogen. Understood? Under chemical reactions, new compounds are synthesized. Under nuclear reactions, new elements are synthesized. Why? Because nuclear reactions are taking place by the involving number of protons and neutrons. Understood? So all the stabilities, everything we'll discuss in this chapter, students. So first of all, composition of the nucleus, like I already said in introduction, what the nucleus is made up of? Nucleus is made up of protons and neutrons. Protons are the positively charged particles, neutrons with no charge, neutral, electrons with negative charge. Okay, so nucleus is made up of protons and neutrons, students. The fundamental particles present in the nucleus of an atom are called as protons and neutrons. These particles are regarded as the building blocks of the nucleus. That means, which is nothing but the nucleus is made up of protons and neutrons, that's it. So nearly 30 particles are identified in the nucleus. All these particles are formed by the interaction of the protons and neutrons. Students, listen. So as of now, the three main subatomic particles are protons, electrons and neutrons only. So this chapter is nuclear chemistry. We consider mainly nucleus only. That doesn't mean electrons were there, but we consider about the nucleus only, students. And these are the three main subatomic particles, but still there are more particles present inside the nucleus of an atom, students. They are called as subatomic particles, or for example, gluons, quarks, mesons, antiprotons, positrons. Like that, many subatomic particles are there. Almost 12 particles of matter, main particles, almost 12 particles are identified, and they are also made up of many. Understood? But ultimately, the three main subatomic particles are protons, electrons, neutrons. This chapter is a discussion about protons and neutrons together called as nucleus, by the particles together called as nucleons, right? So a nucleus species or nuclide, together the particle is also called as, that species with protons and neutrons is also called as nuclide, is represented with atomic number as subscript and mass number as superscript to the left side of the chemical symbol, students. Atomic numbers, mass number. Let us define these two first of all. Atomic number means the number of protons present in an atom is called as atomic number, indicated by Z. That is atomic number. What is atomic number, students? Atomic number indicates number of protons. Only protons? Not only protons. It also indicates number of electrons in a neutral atom. Why? Because in a neutral atom only, protons are equal to electrons. Understood? So atomic number indicates number of protons. In general discussion about nucleus, so let us consider protons only. And what is mass number? Mass numbers indicates Sum of protons plus neutrons. Sum of protons and neutrons. Sum of protons and neutrons is called as mass number. If X is the element symbol, students, look at where the mass number is indicated. Superscript top position is called as superscript position, and where the Z is indicated, subscript down position. So that is atomic number. What is atomic number? Protons in an atom. What is mass number? Protons plus neutrons. If you want to find the number of neutrons, how can you find? Answer, just think. Students, atomic number is protons, mass number is protons plus neutrons. I want to know the number of neutrons. How to find? Simple. Mass number minus atomic number indicates number of neutrons. Yes, sir, students, right? That's how we have in the coming slides also we have that discussion. So, a distinct kind of an atom or nucleus characterized by a specific number of protons and neutrons is called as a nuclide. That means a particular number of protons and neutrons present in the nucleus of an atom is called as a particular nuclide. So, next, isotopes. Based on these types of nuclides, based on these types of nuclear species, we have the following classification: isotopes, isobars, isotones. First, isotopes. What are isotopes? Atoms of or elements with same atomic number but different mass number. So here the definitions are according to the nucleus. So nuclides having the same atomic number, nuclides having same atomic number and different mass numbers. Students, answer first of all, nuclides. Nuclides means a nuclear species with specific number of protons and neutrons. Okay, they have same atomic number. That means these nuclides belong to the same element or different element. Same atomic number means same element only. Sir, if number of proton changes, element changes. Remember, if number of proton changes, element only changes. That means here nuclides having same atomic number. That means same element. The nucleus species of different atoms belong to the same element only. Why? Because same number of protons and different mass number are called as isotopes. So where is this difference is coming from? Atomic number is same, mass number is getting differ, but by which subatomic particle this difference is coming from? This difference is coming from based on the number of neutrons. Is it protons? No, proton changes, element only changes. Understood? So, but why? Where is the difference coming from? Based on the number of neutrons. For example, look at the examples, students here. 1H1, 1H2, 1H3. All these three examples comes under which element, students? 1H1, which element? Hydrogen. 1H2 also hydrogen. 1H3 also hydrogen. Why? Because what is the atomic number? Subscript position 1. 1H2 1, 1H3 1, 1, 1, 1. All contains one proton, one proton, one proton. Yes or no? But look at the mass numbers. The mass numbers are getting different. Yes or no? What's the mass number? 1 here. What's the mass number here? The mass number becomes 2. For the third atom, mass number becomes 3. Yes or no? Mass number is the sum of protons and neutrons. In 1H1, how many neutrons are there? Students, is it 1? No, 0 neutrons. Yes sir. What is mass number? Protons plus neutrons. Already one proton is there, no neutrons. That is simply mass number is also 1. 1H2, how many neutrons are there? 1 proton, mass number is 2. 2 minus 1, I already gave the relation in the previous slide. Yes sir, 2 minus 1, 1 neutron is there. 1 proton is there. So 1 plus 1, 2. In 1H3, how many neutrons are there? 2 neutrons are there. 1 proton is there. 1 plus 2, 3. Understood? So which subatomic particle is the reason for the difference in mass numbers? Number of neutrons. Definitely they have different nuclides or not, students? This is 1 proton, 0 neutrons. 1 proton, 1 neutron. 1 proton, 2 neutrons. Understood? So they are called as isotopes. We have other examples also. Chlorine 1735, chlorine 1737. And carbon 12, carbon 13, carbon 14. These are all carbon only. But mass numbers are different. This mass number is different because of its subatomic particle, number of neutrons. These species are called as isotopes. Next, isobars. This time nuclides, same mass number but different atomic number. Nuclides having same mass number but different atomic numbers. Now answer, these nuclides, they belong to the same element or different element? Different atomic numbers means definitely different elements. So look at here, argon, calcium, different elements or not? How can we say different elements? Why? Because look at the atomic number of argon, 18. What is the atomic number of calcium? 20. Different elements. But what is the mass number? 40. What is the mass number here? 40, 40, 40, right? So here iron 58, nickel 58. Look at the iron atomic number, 26, 27. Nuclides with different atomic number but different mass number but having same number of neutrons are called as isotones. What are isotopes, students? Nuclides with different atomic number, different mass number, but having same number of neutrons. That type is called, comes under isotones. Look at his silicon, phosphorus. What is silicon atomic number? 14. Phosphorus 15. Different atomic numbers. Silicon mass number is 30. Phosphorus 31. Different mass numbers also. How to find the number of neutrons? Mass number minus atomic number. 30 minus 14, how much? 16 number of neutrons. 31 minus 15, 16 neutrons. Understood? These two particles, they have same neutrons or not? This is one more classification called as isotones. We have one more example here. Sodium 11, 23. 11 is atomic number, 23 is the mass number. Magnesium 12, 24. 12 atomic number, 24 mass number. So how many neutrons are there? 23 minus 11, which is how much, students? 12. 24 minus 12, 12. Same number of neutrons or not? In other examples also. These particles with different atomic numbers, different mass numbers, but are having same number of neutrons. This is one more classification of nuclides called as isotones. Isotopes, isobars and isotones. Next, nuclear isomers. This is also one of the classification only, students. Nuclear isomers means this time atomic number is same, mass number also same, neutrons are everything same element only, but based on energy, it can show different property. That classification is called as nuclear isomers. Isotopes, neutron different, yes or no? Isobars, what is the different? Protons different, yes or no? Isotones, both are different, number of neutrons are same, yes or no? Nuclear isomers, what is the difference? Energy is the different here. This is energy difference. Nuclear isomers were introduced by Otto Hahn. Nuclides having same atomic number and same mass number, that means same atomic number, same element only ultimately, but with different nuclear properties like radioactive nature, magnetic momentum are called as nuclear isomers. Look at here, look at the examples. Br 3580, Br 3580. Both are same, right? Why do we need to classify? We need to classify. Why? Because both don't have same energy. You can see here in brackets small g. What does it mean? Ground state. M, small m, metastable state. Sometimes we can also say excited state also. That means if you provide more energy for an atom, the electrons become so excited, yes or no? Not only electrons, even the nucleons also, students, having more energy comes under this metastable state. Metastable state means, remember, if any nuclear species, if less energy, is it more stable or less stable? A nuclear species with less energy, what is your guess? More stable or less stable? Less energy refers more stability, remember. More energy refers less stability. Students, understood? Less energy refers more is the stability. More is energy, less is the stability. Yes or no? Simple statement. So here, ground state, metastable state. Ground state having less energy, metastable state having more energy. Now answer, students, these two elements both belong to the same element, bromine only. Are they stabilities, or do they have the same stabilities? No. Which is more stable? Ground state bromine is more stable than metastable bromine. So do they exist? Yes, they are also exist in the nature. They are also exist in the nature. Then metastable bromine, if it is not unstable, it becomes into, what happens? Yes, correct, students. It is highly unstable only, but it also has some lifetime. In that lifetime, it exists and it converts into the most stable state because of having high energy. So the nuclide present in the ground state will have less energy and more stability. So it is non-radioactive in nature. Yes or no? Does it need to emit its radiation, radioactive decay? No, no need. The nuclide present in the metastable state will have more energy and less stability, so it is radioactive in nature. So when it comes to the radioactivity, the difference is there or not? So this difference comes under a category called as nuclear isomer. This time, what is the difference? Mainly energy, right? Radioactive isotopes. Okay, students, listen. You already know, you already have the clarity about isotopes. Yes, sir. What are isotopes? Atoms with same atomic number but different mass number. They are called as isotopes. So we also have seen different isotopes. Also, these are all the examples of isotopes. Are all these isotopes, are they stable? What is your guess? All the isotopes are not stable, students. Some are highly unstable also. Why, sir? Why they are highly unstable? Why? Because Some isotopes, they have excess neutrons than they required. Some have excess neutrons than they required. That is what the radioactivity coming. Radioactivity coming because of the instability in the nucleus, they emit radioactive decay, radioactive emissions. So let's see what are these radioactive isotopes. Nucleus of these radioactive elements changes as emission of radioactive particles. That means these subatomic particles only, students, alpha rays, beta, gamma, or energy occurs. As a consequence, these radioactive elements may change into new elements. As if particles are changing, if proton is changing, ultimately when a new element forms, if neutron changes, does it form into new element? No. If electron changes, new element? No. When which subatomic particle? Number of protons. If proton changes, remember students, proton changes, element changes. So here nucleus of these radioactive elements changes as emission of radioactive particles. What are these radioactive particles? In the coming discussion in this chapter we will discuss. Or energy occurs. As a consequence, these radioactive elements may change into new elements. This nuclear change, is a nuclear change only, students. Nucleus, from where these particles are changing? From the nucleus only, protons and neutrons. This nuclear change is totally different from the changes occurring in any chemical reaction. Considering the previously, where valence electrons are transferred, I already explained about nuclear reactions and chemical reactions difference in the beginning only. So once again, where the valence electrons are transferred or shared between the different elements and the nucleus remains unchanged, right? In the chemical reaction, students, which subatomic particle participating in the reaction? Electrons. If a nuclear reaction happens, is there any change in the nucleus? No. Hydrogen gas combines, reacts with oxygen gas, produces H2O, water. Is there any change in the nucleus of hydrogen in water? Is there any difference between hydrogen atom and the hydrogen atom in water molecule? No. As a whole, it's a different molecule, that's okay. But atomic level, in the nuclear level, there is no change. Understood? Why? Because chemical reaction doesn't happen by considering without participating protons and neutrons. By participating with subatomic particle, electrons only. How? By losing electrons, by gaining electrons, or by sharing electrons. The energy emitted or absorbed in the chemical reaction is much less than emitted in the nuclear reactions, right, students? In the chemical reactions, all energy changes takes place. So we all know exothermic reactions, endothermic reactions. But when we compare the energy differences, the energy emissions in the nuclear reactions to the chemical reactions, nuclear reactions takes place by the release of enormous amounts of energy. Think about nuclear bombs, atomic bombs, Hiroshima and Nagasaki. Just think about the impact which is created by these nuclear bombs. Understood? To remove an electron, we need to provide high energy. To remove one electron, we are talking about the nucleus. If we disturb the nucleus, just imagine the amount of energy, enormous amount of energy, students. 1 kg of uranium can destroy a normal city also. If we can disturb the nucleus of 1 kg of uranium, enormous amount of energy will be released by these subatomic particles present in the nucleus. They are called as nuclides. Understood? That's why this chapter, this discussion, this research about the nucleus is mainly because of energy purpose only, and the future is mostly based on nuclear energy only, students. Enormous amount of energy is there, so we have to utilize it in a proper way, in a safe way. The future is mostly nuclear energy only, remember. So next, size of the nucleus. This is one of the part under this discussion, size of the nucleus. So size of the nucleus, students, is mostly size or radius. Is the based on on what basis? Based on the number of particles present in the atom. Which particles? Protons and neutrons. So the size of the nucleus is directly proportional to protons and neutron number. What is that proton and neutron number? Is called as mass number, students. This relation is given by the scientist Rutherford. In the nucleus of an atom, protons and neutrons will be present. So the size of the nucleus must be related to the sum of protons and neutrons, or not? Obviously. So the Rutherford gave a relation between the radius of the nucleus and the mass number. According to the Rutherford, radius of the nucleus is directly proportional to the cube root of its mass number. This is the relation. Radius of a nucleus is directly proportional to the cube root of its mass number. So if we equate these two, we'll get a constant. This constant R naught is called as a proportionality constant. Yes or no, students? If you equate any changes, we'll get a constant. What is the meaning of that constant? That change is happening at a fixed rate. So here the constant value is also given, students. This is the relation where you have to remember. Sir, what is the derivative? No need. Just remember the relation, students. This comes under completely quantum mechanics, classical physics, nuclear physics. Just note the relation. That's it. So we have a value for the constant also. What is the value? Its value ranges from 1.25 into 10 to the power of minus 13 centimeter or 1.50 into 10 to the power of minus 13 centimeter. So in general, for calculation purpose, in between, we have to consider this number. You have to consider for calculation purpose 1.40 into 10 to the power of minus 13 centimeter. That is the relation between the mass number and the size of the nucleus given by the Rutherford in this relation. Right, and these are the constant values you have to make a note about. So nuclear stability, correct? Students, during the beginning of the universe, just guess what is the first element to exist? Hydrogen. Why? Because it contains one proton. Yes or no? Does it contain any neutrons? Is there any chance for instability? No. Simply one proton, one electron is revolving around that. Then how do we have all these elements? By combinations of different number of protons and different number of neutrons only. Yes, sir, mainly protons. Right, students? We have how many elements? 118 elements. And every element has a certain number of isotopes also. Yes, sir, no? So different number of nuclides are also present. So all these are stable because of what purpose, what reason? For example, helium contains 2 protons, 2 neutrons. 2 protons are there, 2 neutrons are also there. So how it is stable? Protons and protons should repel with each other. Yes, sir, students? But how it is there? Understood what I am saying? Proton, positive charge, they should undergo repel. How they can together exist in the nucleus? That we'll discuss in this nuclear stability. Not only helium, all the elements. Element with atomic number 118, artificially synthesized element, organeson. It has 118 protons and more than number of neutrons also. Of course, it is highly unstable. Then how can we make that number of protons together to create that element even? How it is possible? So there are some factors are there for this nuclear stability. What are the factors? Mass defect and binding energy, N by P ratio, neutron to proton, students. Magic numbers. These are the factors which influences the stability of the nucleus. So let's see. If a nucleus is not stable, what does it become into? Radioactive element. Sir, it emits its subatomic particles, it emits the radiation, radioactive decay. Understood? That's what. So first of all, mass defect, students. Mass defect, the difference between the calculated mass of an atom and the actual mass of an atom is called as mass defect. That means the calculated mass and the real mass. What is this calculated mass and what is the real mass? How does it happen? I will explain that relation. Listen, first look at the relation. Mass defect delta m, small m, equal to calculated mass minus the real mass. Calculated mass minus real mass. Sir, what is calculated mass and then what is the real mass? Let's see that discussion. So calculated mass. Students, a mass of an atom is based on the mass of its subatomic particle. The mass of an atom is based on the mass of protons and neutrons. Mainly, electrons mass is very least, very negligible, almost non-considerable. Understood? But here, for calculation, we are considering the mass of electrons. Let's see the relation. Z indicates atomic number. You already know atomic number indicates number of protons and number of electrons in a neutral atom. So mass of electron plus mass of proton plus how to find the number of neutrons? Mass number minus atomic number. Yes or no? Look at the relation. A minus Z. A indicates mass number, Z indicates atomic number. So A minus Z equal to mass number. So mass of electron plus mass of protons plus mass of neutron. What is that? Calculated mass of an atom. Yes or no? Right. So like together we can have the shortcut notations. Mass of electron Me plus mass of proton Mp plus A minus Z Mn, mass of neutron. Okay, clear this step? Mass of electron plus mass of proton, just we combine. Z indicates atomic number plus A minus Z Mn. Clear? Mass of electron, mass of proton together is taken as Mh. Mh means mass of hydrogen. Yes or no? Hydrogen contains 1 proton, 1 electron. Simply hydrogen atom mass is the mass of 1 electron, 1 proton or not? Understood? That's why directly taken as Mh. And this, in this expression there is no change. And sir, why it is Z here? If you want to calculate the mass of helium, you have to write 2 here. Into 2, yes or no? If you want to calculate the mass of an element with atomic number 100, into 100. Understood, students? Simply we have taken mass of electron plus mass of proton as one entity, that is mH, mass of hydrogen, into any number will become the mass of that element, proton and electron, right? So here mH is the mass of hydrogen atom. Why? Because it contains one proton, one electron. Mass difference of an atom. Now let us have the complete relation. ZmH plus A minus ZmN minus, this is the real mass m. So look at here, the values are also given, students. mH value, what is mH value? Mass of hydrogen, right? Mass of proton plus mass of neutron. How much? 1.007825 AMU, means atomic mass unit. What is it? That in the coming slides, in this video only we'll discuss that. That is the in AMU, mass of one hydrogen atom, proton plus neutron, and mass of neutron 1.008665 AMU. Mass of neutrons are slightly heavier than protons, students, remember. So the difference in the mass is converted into energy, and this energy is used in the formation of the nucleus. This is called as, students, this is called as binding energy, one of the main point for the stability of the nucleus. What is this energy is called as? Binding energy. How this binding energy? The difference, we already have said the calculated mass. The calculated mass is because of mass of proton, mass of electron, mass of neutron in the atom. And the actual mass, there is getting difference, right, between the calculated mass and the real mass. Where is the difference is getting utilized? The difference is getting utilized for the stability of the nucleus. Sir, how mass and energy? You should remember one famous equation, famous relation, which is given by the Albert Einstein. Mass energy relation, yes or no? E equal to mc square. We have that discussion also. So this difference in the mass is converted into energy, and this energy is utilized in the formation of that particular nucleus, like helium or helium isotopes, lithium or lithium isotopes, till 118 also. Understood? This difference in the mass between the calculated mass as well as the real mass, and this mass is converted into energy, and this energy is utilized in the formation of the nucleus for the stability of that nucleus also. So students, so we have to define this binding energy. So once again, according to Einstein equal to mc square in general, students, one atomic mass unit equal to one AMU equal to how much? 931.5 MeV, means million electron volts. This is the relation between mass and energy relation. So to find the value in terms of binding energy, how much we have mass defect in AMU. Into this electron volts, we'll get the binding energy. Binding energy equal to mass defect into, sir, why this? Why? Because 1 AMU equal to how much, students? 931.5 million electrons. Sir, how it is possible? That also we have the discussion in the last slide. I'll explain how this relation came. Understood? So binding energy, that means we are converting mass into energy scale. On what basis? In terms of MeV, million electron volts. How to do that? First of all, we have to consider 1 AMU, and we have to 1 AMU will get delta M in AMU or not. That AMU into 931.5 MeV, million electron volt, will get binding energy. So what is binding energy? Let's see. Is defined as, binding energy is defined as amount of energy required to break the nucleus into its constituent nucleons. That means a stable nucleus is there. To break that nucleus apart, that means to break all the subatomic particles apart, we need to provide some energy, right, students? Why? Because they are already stabilized by that energy. That energy is called as binding energy. It can also be defined as the amount of energy released when the nucleus is formed from the required number of nucleons. By the combination, all these nucleons means what? Protons and neutrons. Are they present in the nucleus separately? No, they are not present separately. They all together exist as a single entity. That's why we're calling it as a nucleus. Yes, sir, students. For this nucleus, for the formation of this nucleus, it releases some amount of energy, right? That energy is called as binding energy, and this energy is getting created from where? From the mass of the particular nucleons. This mass converted into energy. That's why the calculated mass is always different from the actual mass. Which is more? Calculated mass is always higher than the real mass. Why, sir? Why? Why? Because in an atom, the real mass, some of the mass is getting converted into energy, and this energy is utilized for the stability of the nucleus, and these are all the relations. And these are the units conversions also. Got the clarity, students, about binding energy? One of the main reasons for the stability of the nucleus. So when the total binding energy is divided by the mass number, binding energy per nucleon, that means per subatomic particle, per proton, per neutron, we get that energy is called as average binding energy. So binding energy per nucleon, which is called as average binding energy, is equal to the total binding energy by the mass number. Yes or no? If there are 10 particles are there, protons and neutrons, by 10. If 20 are there, by 20. Then what we'll get? We'll get the energy of each and every nucleon or not. Nucleon means proton plus neutron. So for every proton, for every neutron, we can calculate the binding energies also. This is the relation for that. So next, students, so N by P ratio, neutron per proton ratio. So students, listen, there is no fixed number. There is no fixed number. Don't think mass number is always not the same, double of atomic number, not every time, students. It all depends upon the energies which are needed for that stability of the nucleus. So answer, if the N by P ratio, if it is more or if it is less, when the atom becomes more stable, when the nucleus becomes more stable, students, we have one relation, we have one ratio of difference, like for the chemical reactions also, whether to form ionic or covalent, we have one difference in electronegativity, SR 1.7. So here also for the stability, based on N by P ratio, neutron proton ratio, we have one number. The ratio between the number of neutrons and protons present in the nucleus is called as N by P ratio. For the stable nuclides, N by P will be in between 1 and 1.6. If that ratio, if it is in 1 and 1.6, then the nucleus species, then the nuclide is said to be stable. If it is more than that, that means if more neutrons are present, the nucleus becomes unstable. Yes or no? The nucleus becomes unstable. More neutrons, more than required. So N by P ratio is maximum for tritium. What is tritium, students? Tritium is 1H3. How many neutrons are there? 2 neutrons are there. How many protons are there? 1 proton. What is the ratio? 1:2. Yes or no? There are 2 neutrons per 1 proton. So maximum for tritium, which is equal to 2, which is highly unstable. Unstable means, don't consider chemical reactions. Nuclear, in terms of nuclear instability, means radioactivity. We'll discuss what is radioactivity. We have the separate discussion. Radioactivity, it emits their own subatomic particles, energies, everything. So nuclides having high value of N by P undergo nuclear decay and to become more stable. Ultimately, they want to become into more stable form. So right, next. Third factor is magic numbers. This is given based on a model, nuclear shell model, students, by the Wigner, by the scientist Wigner. Nuclides having these numbers 2, 8, one second. Nuclides having 2, 8, 20, 28, 50, 82 and 126. Either that number of protons or that number of neutrons, or protons and neutrons, both that number becoming stable. These number of protons, either protons or either neutrons, or both protons and neutrons with these numbers in the nucleus are said to be more stable. Sir, why? I already have said, based on one theory, we don't have that discussion here. The theory is called as nuclear shell model. So when compared with their neighboring nuclides, that means with the remaining nuclides, these numbers are called as magic numbers, students. These numbers are called as magic numbers. Why? Because with these numbers of nucleons, the nucleus become more stable. If a number of protons and neutrons are both or magic numbers, then the nuclide is more stable. For example, if the atomic number comes under only this number, not the number of neutrons, that is more stable and that have maximum number of isotopes also. If only Z is a magic number, it will be having maximum number of stable isotopes. That will, for example, tin with atomic number 50, it has stable isotopes. It has almost how many? 10 stable isotopes. That means the nucleus species with these numbers of either protons or neutrons, or both protons and neutrons also becoming more stable. So these numbers you have to remember as magic numbers, students. So ultimately we are discussing about the stability and instability of the nucleus. So these numbers are more stable. What these numbers? Neutrons or protons, or both neutrons and protons also with these numbers present in the nucleus. They are called as magic numbers based on nuclear shell model. We don't have the discussion about nuclear shell model. So remember that numbers. Mass to 1 AMU, mass equivalent to 1 AMU, atomic mass unit. That means the conversion from grams to 1 AMU. How to convert? we'll get this relation from stoichiometry. Yes, sir, students, how can you define 1 AMU? 1 AMU can be defined as 1/12 the mass of one carbon atom is taken as 1 AMU. 1/12 the mass of one carbon atom. So let us find the mathematical relation. 1/12 into mass of single carbon atom. How can we find the mass of single carbon atom? What is the mass of 1 mole of carbon atom? 12 grams. Yes or no? 12 grams is the mass of 1 mole. 1 mole means how many? 6.023 into 10 to the power of 23 atoms divided by that number. You will get the mass of single atom or not? 1/12 into weight of one atom. How can you find the weight of an atom? 1 mole of atoms by the number of moles. Understood? 1 mole. The mass of 1 mole of atoms which is 12 grams by 1 mole, which is 6.023 into 10 to the power 23. 12 and 12 will be cancelled out. So 1 by 6.023, this number equal to how much, students? 1.67 into 10 to the power of minus 24 grams. This is taken as 1 atomic mass unit. So this is the relation between 1 AMU and the mass in grams. So next we have the relation with AMU and energy also. In the previous slides we have the discussion about MeV, million electron volts. Yes or no? Let's see the relation. And this relation is coming from E equal to mc square. E equal to mc square. So mass in terms of AMU, how much, students? 1.67 into 10 to the power of minus 24 grams. And C indicates speed of the light, how much? 3 into 10 to the power of 8 meters per second, or 3 into 10 to the power of 10 centimeters per second whole square. C square, na? So we have a value of how much? 1.492 into 10 to the power of minus 3 ergs. So 1 million electron volt equal to this number of ergs. So these many ergs means how many? Simple cross multiplication. So energy equal to 1.492 into 10 to the power of minus 3 by 1.602 into 10 to the power of minus 6. How much, students? How much we are getting? You can see the number, which is equal to energy 931.5 million electron volts is the relation between AMU and energy. So 1 AMU equal to these many million electron volts. Got the relation? Got the relation between AMU and mass equivalent in terms of grams, and 1 AMU as well as million electron volts. So students, this chapter is completely about the nucleus, nuclear models, nuclear stabilities, radioactivities, radioactive emissions. But if you want to consider the whole derivations, means we don't get all these derivations. You have to remember the numbers, you have to remember the values, that's it. And you have to learn the concept, what is happening, why it is happening there. So clearly we discussed in this video about stabilities of the nucleus, yes or no, N by P ratio, magic numbers, mass defect ratio and all, as well as the composition, the classification of nuclides, everything. And in the coming videos we have the discussion about radioactivity, types of radioactivities. So that we'll discuss in the next video. That's it about nuclear chemistry introduction in this video, students. I hope you got the clarity. So thank you.